Thank you very much. Okay there. Hello everybody, my name's Ayckbourne. I'm a PhD student at the University of Manchester. And today I'm going to talk to you about deep water basin formation, more specifically deep water basin formation in foreland basins in epicontinental settings. Now that might be interesting to a lot of us here because many of us who study deep water processes in outcrop often are actually studying rocks that were formed in epicontinental settings, as a contrast to passive margins, which don't actually outcrop that well or that frequently. So when I mean deep water basin initiation, I actually mean the initiation of a shelf slope profile and a progradation of that profile. And sort of our basic understanding of this is that if we have enough accommodation space in the water column and enough sediment supply, we can basically generate this profile by depositing most of the sediment closer to the terrestrial or towards land. And that differential sedimentation generates a mounded relief, and that eventually will prograde and even aggrade if there's enough accommodation space within the water column and enough sediment supply. The other method is by a structural initiation. So you have that accommodation space and profile generated by a normal fault in this example, and we have progradation of that shelf slope profile if sediment supply is sufficient enough. And if there isn't enough sediment supply, we just end up with we still have a shelf slope profile, but it's actually really just a structural feature. Now, these understandings come from passive margins because they're often from seismic studies. And because of that, these are quite static models. And so we can make some sort of novel assumptions. For example, if I were to take the base of this basin here and take a line to the top of the clinothem, we could make some assumptions about the water depth at the time of deposition. Now, I'm going to give you some examples of why that might not necessarily be true in tectonically active settings. So that leads me on to the study area. So I work in the Spanish Pyrenees. More specifically, I work in the Aínsa basin. And so the Pyrenees were formed as part of the Alpine orogeny. And in this location, we had the collision between Iberia and Europe. And on the southern margin of the Pyrenees, we had this sort of south virgin, south propagating foreland basin that had an axial sort of depositional system that was shallow in the east and had fluvial deltaics in the east, which delivered sediment towards the west to a deep water basin over here at Hacker. And that deep water setting is joined by a slope and canyon system, which today we call the Aínsa basin. So here's a sort of diagram that shows you the stratigraphy of the Aínsa basin. It's actually had any sort of structures or everything else removed. It's really just supposed to be used as a correlation panel, really. And it shows you sort of the units that's in the sort of slope system that correlate to their sort of lateral fluvial deltaic systems. And basically our understanding is that we had a initial ramp system that went from east to west, and that was then incised by a canyon, and subsequently we had progradation of a delta and a shelf that kind of passively infilled this canyon. And this kind of repeats multiple times to form the stratigraphy of the Aínsa basin that we know today. So I just mean to say that actually in this talk, I'm actually going to be talking about the earliest deposits of the system, so the point at which the Aínsa basin was truly formed. And so our canyon system here is the Atiart Canyon, and the system itself is called the Foradada system, and it's named because of a channel complex that exists within the Atiart Canyon. So this is sort of the main meat of what I'm going to be talking to you today. It's the field map from that area, and it's there's quite a lot going on here, but actually before I move on and show you a sort of more simplified version of this, there's just a few things that are quite important to point out. So we have two major structures. We have a fault in the east and a frost fault in the east and a frost fault in the west. We also, from the form lines, can see that we have these big footwall synclines inside those frost faults. And the other thing, sorry, to point out is that plunge here is actually to the south. So what we really have is the youngest deposits at the bottom of the page and the oldest at the top of the page at the moment in this orientation. Helioflows here are from the southeast towards the northwest, except when we get close to these structures, we get some deflection of ripples that deflect more westward away from these structures, which is our first indicator that actually these structures may have been active on the seafloor at the time of deposition. And moving on to the other big sort of portion of data set I'm going to talk to you about today, which are the log sections that I've done through this area. But like I said, everything's upside down. So if you hold on to your seats for a moment, I'm going to rotate the map so that stratigraphy is the right way up. And we can basically take these series of log files that are taken and see them as 4 continuous log sections. This one in the east being the longest, which makes up about 900 meters of stratigraphy. Now, before I do move on, I'm just going to quickly talk about our fasces. So if you remember that diagram I showed you earlier on, we had that in the green at the bottom of this page here, we have this, what was interpreted as a ramp feature. So it was predominantly sort of shallow carbonates towards the west. And then as we go further towards the east, we kind of correlate across to these sort of very marly structureless mudstones. Working our way up in the greys, we have our mudstone deposits, and with their dashed, they're quite deformed by MTDs. In yellows, we have our heteroliths, so turbidites interbedded with mudstones. And if you look into the the west side of the map here, but to the right, we have our thick amalgamated high-density turbidites, in this case making up a channel fill, and this is actually the Foradada sandstone system over here. And interesting enough, it's actually located in the footwall syncline of that thrust that we mentioned. So yet another indicator that maybe there's some sort of topography being generated on the seafloor that are forming conduits for these channels. And the last thing I'd point out is this: there's a purple line here that makes that boundary between the green and the that infill, and that was interpreted as the Atiart Canyon contact. And so it's supposed to be this deep incisional surface that's then later been passively infilled. But if you look at the form lines, you might actually notice that that can't really be true. We have this fold structure in here that has overall growth from the bottom to the top, which means it's steeply folded or tightly folded at the base and not so folded near the top. And these form lines actually completely transect this surface. So they tell us that actually the deep water deposits have to be more coeval or more closely related to their sort of lateral shallow deposits. So just quickly, I can't spend too much time on this because I do need to move on, but this is these are those log sections that I mentioned, and we're going to be focusing on the two on the right. And really, these are just fasces association logs, really. So these will log in detail, and then we've just grouped them into key fasces associations. And as they say, the two on the right are going to be used as our main data set. So what I've done here is actually simplified that map down to a down plunge cross section that's really just showing the key things that need to be seen in the map. Again, we have that thrust towards the east and that thrust towards the west. And what we can see is that as we move up our stratigraphy, we gain more and more of these deep water deposits. And that's because this contact here between the shallow deposits and the deep water deposits retrogrades from west to east up into this phase. And then actually we have a later phase where the shelf margin actually reprogrades forward, and we have the deposits that are kind of coeval with this. Now there's a fundamental difference between the type of deposits that we get in the lower portion, which is syn retrogradation, and with the upper deposits, which are syn progradation. And so if we compare the two from those two logs that we took, what we actually see is that in the lower deposits, which are these pie charts here, so the log on the right and the log on the left, and what you'll notice first of all is that this slope is mudstone dominated. That's true throughout the slope. But if we compare this to the next package up, what we actually see is that we have a reduction in the heteroliths, the sandstones overall. So if we compare these two charts, we have less sandstones, and if we compare these two charts, we have less sandstones in the upper portion than we do in the lower portion. And also the types of MTDs, or the amount of MTDs, significantly reduces between the lower portion and the upper portion. And we think that those two things are intrinsically linked. That's probably because as we have more MTDs generate rugosity on the slope, and therefore generating topography, and that topography often traps more sediment. And when that topography has been healed, our flows tend to bypass more easily, and we really only have the tails of turbidites being deposited or pelagites being deposited. And if there weren't any MTDs in the first place, then we are more likely to have a sort of more bypass-dominated system. And therefore, we can sort of assume that the lower portion was more sort of unstable, and then we have a later portion with coeval with the progradation that is actually a slightly more stable slope and therefore less coarse-grained. There's another real fundamental difference between the types of deposits that we get between the lower and the upper portions. So between the syn retrogradation section, we tend to have these sort of more classic Bouma sequence style thin-bedded turbidites, which are generally normally graded, so from coarse to fine-grained. They tend to be planar laminated near the base and ripple cross laminated and rippled at the top. But when we get to the upper portion in the sort of syn progradation section, we get very different turbidity flow deposits. We actually end up with sometimes thicker deposits, but they end up being more frequently inversely and normally graded multiple times throughout the bed. And we tend to jump between planar lamination to ripple lamination back to planar lamination multiple times. And that seems to suggest sort of quite high changes in the flow velocity. So we're jumping between the flow regime. And therefore, we think that that's most likely tied to the sediment being derived more closely to those deltaic, that deltaic input. So at this point, I can sort of summarize some of the things that we've discussed here. So we saw that we had up to 900 meters of slope deposits in the Foradada system. And if we take that example I gave you very early on, some of us might take that bottom of the basin to the top and say, well, that therefore must mean that we had 900 meters, a 900 meter piece of accommodation space that was then later filled by this infill. But what we actually see is that we had this sort of simultaneous shelf aggradation and retrogradation, which led to a feature that appeared to be this big, deeply incising erosional surface. But actually, in truth, we've seen that it was actually coeval with the deep water deposition. And therefore, in truth, there was likely never any real sort of major topography on this bit of sea floor. Really, all of this surface was already buried, and sedimentation kept up with this aggradation and retrogradation. And lastly, we saw that deposition coeval with shelf retrogradation was generally characterized by greater amounts of sandstone accumulation and greater slope failure, while the deposits that were coeval with progradation were much more stable and mudstone dominated. I think I've left enough time at the end here for questions, but I'd like to thank you for your time, and also a quick thank you go to my field assistants and the sponsors of the NOTE CDT. Yeah, any questions?
Hey. Great talk. Thank you very much, Leslie. And I just have to look at my question box. It is the way it is, and I see lots of questions coming up from the previous for the previous presenters. So there's still a lively questioning going on. But of course, there's a time delay. You have to type in that particular question, and that takes time. And well, you know how it goes.
Can I ask a question, George?
Yes, sure. Yours. Go ahead.
So yeah, thanks for this beautiful documentation of the field site. Can you? I'm not entirely sure yet whether I understand why you claim that in truth there was likely no significant scar on the seafloor. So yeah. What's the reasoning for this quite bold statement?
Yes. So one of the things we could do here is possibly follow each of the form lines, for example, in this, but actually even if we go back to the map, we follow each of the form lines. Now, in the field, of course, there is some erosion of this lower contact that we saw on the shelf slope contact. And there is obviously, the fact that the shelf is retrograding, there has to be some incision occurring. But if the form lines, the first thing we see is that overall, this is a growth fold. And I have some additional work that I've done, is these logs that actually go towards the center of this fold axis. They show that actually these lower deposits actually do grow towards that axis. So we have thickening towards the syncline, even within the shelf. And of course, it's very clear from the map even to see that that growth continues into the sort of deeper water deposits as well. So we know that this structure is active throughout that time. Whereas if we had an incision followed by an infill, we would expect there would have to be a major angular unconformity between the two. You wouldn't be able to preserve structure in this way. Would you agree with that, or?
Why not? Why I don't see that.
Okay.
Point.
Yes, I mean, so the other major piece, so not presented here, and it's actually part of another piece of work I'm working on. It's actually really looking at that contact in more detail, and we see multiple locations where actually the shelf and the slope interfinger. But that,
Okay.
like I say, I haven't presented here, but there is a famous location here, this scallop-shaped contact that you get between the Atiart Canyon and the field. But actually what you see overlying that scallop is a major progradation of carbonates. And so that specific contact is actually interfingering as well. So there's other points as well.
You got some additional observations of that actual surface to say that it's not a major erosional surface in effect. Okay, thank you very much.
Okay, thank you, Jonas, for the question, and thank Ashley for your nice presentation.